we got the part mounted in the chuck here, and put the end piece in, extended the quill of the tailstock. Now we got to indicate a few things. We got to indicate this flat to set our C0, and then we got to set our Z offset just to make sure that in case all the parts aren't the same length. So first, got to jog this over here. Put my dial indicator in the spindle. Index the B-axis down to 45 degrees. Gives me more clearance over here. Otherwise I'm very close and jogging things in, and I can hit up here in this area. Just a little bit safer to do it that way. I mean, I guess I could put a mag base on here and do it too. I just do it this way. We got to run this back and forth and get the C-axis more or less. I forgot which way I went here. More or less roughly lined up here. For some reason I want to jog that the wrong direction. Try to get this as close as possible because I'm only indicating a short little flat here. I didn't make this end fixture. I think I would have milled a notch down here and made it longer, because that out here doesn't make any difference anyway to the function of the fixture. The B-axis of this machine, or the C-axis and the B-axis, have a little bit higher resolution than most machines. Most machines will rotate their rotary axes to 1/1000th of a degree. This machine will position within 1/10 of 1,000th or 1/10,000th of a degree. So it's actually got 10 times more resolution on its rotary axes. Whether it can actually do that, I guess, is a little bit up for debate. Okay, now I'm going to set my C0, teach 0 here. Hit reset. Now we're on 0 for C. And now I'm going to just double check the Z0 is out here, really, but I know this should be 630 thousandths, I believe. I gotta go check the drawing to be sure. I set my Z0 right on the end of the part on my program, although it would have been actually better in retrospect. I should have set it here, because the dimensions on the print actually come from this location. So what I've been doing is just calculating my Z0 based on this position here by coming up here and setting the indicator on here, and then calculating it back to what would be the perfect dimension to here. But if it isn't perfect on the part, it really doesn't matter, because the actual dimensioning comes from this face in reality. So I'll go over here to my work offset again, and we're going to teach that 0.630 here input. It was only different by a half a thousandth from the previous part, so that's good. I think what I'm also going to do, I'll run back to C0 here. Just going to jog it back there. Somewhere here. Okay. I think I'm going to check the centering this direction, just to be sure, on my fixture offset. Things can change on machines. Even though you think that it should be the same from one day to the next, it actually sometimes isn't perfect. What I like to do is just double check it just to be sure. And it was kind of warmer yesterday and it's colder today here. And maybe things are a little different. So we're going to I'm just going to go by the tail center here. This pretty much has to run on center line. If there's a slight run out in the part itself, in reality I'm going to turn the OD. They left a little bit of stock on these parts for some reason. Probably can't really see what I'm doing here, but very well with this camera, but finding the null position. I should be, oh wait a minute, wasn't actually on center line on the readout on the display. So that's the center line. Now I'm going to need a mirror. Can't see the indicator when I rotate it around back this time. When you're looking in the mirror and you rotated the dial of the dial indicator to zero it, you have to do it backwards from the way you think you should, because it's reversed. It can be kind of confusing. Okay, we get the null position going up and down with the z-axis to get on the top of this radius. We swing this back and forth to get the null position by rotating the dial indicator. I'm going to jog half the distance of the error. Double check everything. I'm not going to worry about tenths of thousandths here, but that's pretty close. Now I'm going to zero that out. That's about a thousandth of an inch. That's about a thousandth of an inch difference from yesterday. See, these things can change. Although that's not out of tolerance or anything, but and it probably would change as the day goes on. and the machine warms up more and everything to some degree. I just like to check it to see where it's at. Wasn't off very much. Part was about a half a thousandth different in length from the previous part, and maybe, you know, when the machine powers up and it clamps, it uses hydraulic pressure to clamp down this tail center, and it might clamp in a different position, maybe, I don't know. Or maybe the ball screw is in that y-axis, it's not the same temperature as it was. It won't let you take a tool out of the spindle of this machine unless it's oriented. So, at this point, we're almost ready to start the program on the next part. Now, for some reason, when they made these blanks, they left 80 thousandths too much stock on the OD here. I'm not sure why that was, but I put a turning cycle in here and have to turn this and reduce it down. It's 80 thousandths, so it's 40 thousandths off each side. You take it in one roughing pass and a finished pass. Now, I found on this copper that it's what works the best is to turn a very high surface footage. In fact, I'm turning 1,000 surface feet per minute on these turning cycle that you're going to see, and the feed rate not too fast for the roughing pass, but then I'm using a finishing tool, a VBMT insert, so I wouldn't want to turn too fast with a 35-degree diamond insert, but I'm tipping you'll see it, but I'm tipping the V-axis at 45 with the tool, and so it has a lead angle coming across here, and I'm turning it backwards towards the tail center. And that was mostly just because of clearance on the fixture and the chuck jaws and everything. The reason I did that, but the lead angle on the insert when it's tipped like this, coming into the work, seems to work better too with this copper. It's I'm speculating that it's thinning the shaving down. You don't want too thick and heavy of a shaving coming off this material, and you want a high surface footage, it turns out, to turn it, is what it's looking like. So anyway, now we're ready to start things, and you'll see what I'm talking about. Here we're coming up on the turning operation that I described earlier, where I've got the tool facing backwards and I'm turning away from the chuck. This also had the added benefit of pulling the shavings away from the chuck jaws towards the tailstock, so they didn't get tangled up in the jaws between that steady rest and the jaws. Oh, by the way, the steady rest here is just setting up there. It's not doing anything at all. It's just you have to put the steady rest up forward with this machine in order to bring the tailstock up forward. So that's why that's that way. I also found that turning a high surface footage, like I said, with a slower feed rate worked better with this copper. And I probably don't have the right tip radius and the right insert. I could have probably had a better chip breaker, and that probably would have helped with the shavings there. But I'm not going to go get special inserts just to turn the one diameter. It's the 1/2-inch 4-flute carbide, just a standard carbide end mill with a 30 thousandths tip radius. And I'm doing this kind of trochoidal adaptive, whatever you want to call it, milling cycle here. And that seemed to work pretty good on this copper. I'm not taking a very deep depth of cut on the side of the tool, and a fairly high speed. And it seemed to work pretty good. I was kind of concerned about this tool. I was thinking I'd have problems, but I'm not having any problems at all with this tool on this copper. I've milled probably, I think this is the third part, and I haven't had any trouble. The tool looks real good still. Haven't even changed the tool. When it's doing the deeper pockets on this end of the part, it's taking pecks down there. So it's kind of taking, I don't remember the depth of the pecks, a couple hundred thousandths at a time and going downward, kind of a helical entry, and then it's doing that tricoidal path as it gets down to each depth. Run the machine while I'm recording this voiceover, so I have to kind of stop the recording and go and start the machine and watch it a little bit. And you probably can hear the coolant pump in the background on the high pressure coolant, maybe, I don't know. But anyway, this roughing was working pretty good. In fact, the whole operation was working pretty good, like I described it in the previous video on this part. I'm really not having any trouble with any of the tools like I thought I might with this copper material. It's working really just the way I planned it, pretty much. Now that I'm pretty much using standard tooling for everything that I can. I had to modify the shanks on some of these end mills you'll see coming up. Not on this one. This one I used the standard 1/2-inch end mill. But on some of the other ones, I had to modify the grind clearance, I guess you might say. You'll be able to see it when they come up. Maybe I'll take photos and put it, insert them so you could see the modified tools. Anyway, like I said, this is doing like a helical entry into the material at a slower feed rate, and then once it gets in there, it speeds up quite a bit faster. Trying to think of the feed and speed. I think I was turning like 5,000 RPM on this end mill, and I was feeding about 50 inches per minute, I think, the actual speed. This is, of course, sped up way faster than it really is here. So there's taking the bulk of the material off in the middle of the part by just going around and around after it mills those 2 slots on each end of the pocket. That's what they call an open-sided pocket cycle in Esprit. Profit milling, they call it on Esprit. It's kind of like adaptive on Fusion. So it combines multiple strategies into one strategy, and they call it profit milling in Esprit. So this is the longest cycle, or tool cycle, I guess you might say, in the whole part. It actually takes about an hour to do that milling on the part. And then come in with a 1/4-inch end mill here, just standard 1/4-inch 4-flute end mill to finish out those smaller pockets. Oh no, first we finish the face here, excuse me. This is just a standard 1/2-inch 4-flute end mill again with no tip radius. Finishes this face. And then the 1/4-inch end mill after this one. That's a pocket milling cycle, but it's just a linear tool path. And Esprit does take into account that you've machined certain areas of the material away, so it doesn't actually cut everything. It skips over the pockets that are already milled. It's a bottom finishing pass, if you will, on a pocketing cycle. I'm measuring the thickness of the part here. Trying to hold this close there because you get mismatches in the tools that are coming up if you don't try to hold that fairly close. This is the 1/4-inch end mill. Starting there's a couple of notches on this end of the part where that longitudinal slot with the full radius at the bottom goes down the length of the part here. And then it's going to mill these shallow pockets in the face here. Now I could reach these with a 1/4 inch end mill because the corner radiuses are 130 thousandths on these pockets, so I could do it with a 1/4 inch end mill. And it's mostly just milling the side walls and getting up closer to the radius that from where the 1/2 inch end mill left off, and then it's just doing a finishing cut on the bottom of the pocket and the wall finish on these. It's also starting those two flats for the 3/8 drill that's going to drill those holes there. Nothing special here, it's just pretty much standard pocketing cycle right here. Most of the rest of this video is sped up 5 times the actual speed of the rest of this. It would just take too long. The whole cycle takes maybe 4.5 hours to do the whole machining cycle of all the tools, and of course that would make a excessively long video. So I sped up almost everything in the tooling, the machining part of this video. And I even cut out sections longer sections. Okay, I got to go over to the machine and start tool again, so I'm going to pause the video and the voiceover. Again, had to gauge the threads and start the machine again. I'm trying to do this while I'm running the parts. Trying to do, multitask here, I guess you might say. Anyway, this is milling these. There's these little kind of rectangular pockets on the end of this part, 4 of them that are at kind of like 45-degree angles. That's what it's milling there. And now it's starting the notch again at the end of the slot, and then doing another one of those little pockets at the angle. And I could reach all this with a standard length 1/4 inch 4-flute end mill, a 3/4 inch cut length. I think I had it sticking out about a 1.25 inches or 1.5 inches from the tool holder, just for clearance reasons, but other than that it's a standard tool. I don't know if showing machine work like this is boring for you to watch. For me, I see so much of it that it kind of gives me that feeling, but I don't know, people that don't see a lot of this, maybe this is more interesting for them to watch than me. But I try to cut out quite a bit of this. In fact, in this video, I cut out quite a bit of it, but I still want to show certain things that are happening so you can kind of get an idea of what's involved here as far as milling these features in this part. But in reality, in this particular tool, I cut out quite a bit. So that's what it looks like so far, which is the bulk of the roughing done. You got to come in with the smaller tools in those 2 pockets on the left-hand end of the part, the chuck end of the part. But I'm just rotating it so you can kind of see what's happened so far. Now this is one of the tools I had to modify, I believe. Yeah, this is the 7/32 end mill, 0.218 diameter, and it can reach the majority of those radiuses and everything in these pockets on the left-hand end of the part. And then I mill these, there's 4 little, there must be some kind of screws that intersect in those square rectangular cutouts at the angles. And this is just milling a counter bore just at the beginning of that hole that's on the part. Right there, you can see it now if you look. So here's the next size tool down. This is a 5/32 end mill. And I ground some clearance on the shank of it as well. And if you remember in the previous video, I talked about modifying the shrink holder, and this is the tool that it needed that modification to clear the wall on this pocket on this side of the part here when it gets down deeper. And this tool is pretty much also finishing the walls, but not the bottom. The bottoms were finished with the 7/32 end mill. So that's those pockets almost done, except that little notch you see right in the middle there on this side has to be done with a 1/8 inch carbide end mill. But I don't do that till after I do these slots on the sides here. So I roughed this down with a 3/8 ball end mill. This slot is a 1/2 inch, a little more than a 1/2 inch wide, say 501 to 502 thousandths wide, and it has a full 1/4 inch radius at the bottom of it. So I didn't really want to run a 1/2 inch end mill directly down, a 1/2 inch ball mill directly down into this material. And it turns out that my idea about that was correct, because even though I mill it, I roughed it out with this 3/8 ball mill, and then I come back with a 1/2 inch ball mill just to finish the bottom radius, so I don't have to stitch back and forth a million times with this 3/8 ball end mill. And that turned out to give me a little bit of a problem, even though I had roughed and finished the slot to the width up above the radius with this 3/8 ball end mill, which it did. That's just roughing. Now it's finishing the walls, the side walls, down as far as it can go with the 3/8 ball mill, bringing the tip of the ball to tangent to the 1/4 inch radius, if you will. And then when I went in here with the 1/2 inch ball mill, apparently the shavings that it was pulling up in the tool got recut or got in between the wall and the flutes of the tool in such a way that in this copper it kind of embedded it in the sides of the slot in such a way that it kind of messed up the finish. And so what I found I had to do is I had to what I'm trying to show is, I don't know if you can see it there, but see those little flakes of material? They're kind of like when it was recutting shavings down there or something, it embedded them into the material again or something. And so what I found I had to do is rerun the finish passes, and that kind of cured that problem on this slot. And it left on the very first part, I kind of left it and tried to sand it, or hit it with Scotch-Brite actually, and tried to sand it, and it was kind of it worked, but it was kind of a pain. So what I did here is I just rerun the finish passes, and that actually made it real nice finish in there. Simple as that, and that's a lot easier than getting in there with some kind of emery cloth and Scotch-Brite and everything. So that's what I did, and so I changed the program and added those cutting cycles in the program. So that's the 1/2 inch ball mill refinishing the bottom of the slot here. So now it looks nice, like it's supposed to look. See, without those little shavings kind of embedded back in the surface of the material. It's kind of like when you take a cut with a face mill and it drags the back of the tool over the work, and it kind of leaves a a funny finish, or like you're turning without the right service footage or something. That's kind of what it looked like in there before I did that. So here's a 1/4-inch ball end mill, just rounding off the sharp corners there. There's a radius called out on the print for this. And I had this cycle going. I didn't really, you see how it's raising up at the end of each pass? I didn't like that, so I kind of changed this and increased the feed rate because it was taking longer than it should have. This is what I do often. I run the program, I make the program on the computer and I run it, and as I'm running it, I kind of note down areas I don't like in the program, and then I go back and I make those edits and reprocess the code. And on a part this complex, you usually go through about 4 or 5 of those iterations of the program before you get it the way you want. It's been my experience. Sometimes more, depending on the complexity and how many mistakes you make in the program sometimes. So that's the way it looks so far. This is basically the part finished machine. Oh, except for that radius, excuse me. There's an 1/8-inch end mill, a 1/16-inch radius in that corner, the vertical corner. I don't even know if that's necessary. I would wish people that design parts would have to machine them, and they'd understand that it's kind of a pain to put a 60 thousandths radius or 65 or whatever it is on this part up and down almost an inch of corner distance there, like I'm showing with that wrench there. If that's not necessary, it would sure make it a little bit easier not to have that. Or even those radiuses in those corners, if they could increase them. So this is the only tool I could run without coolant for the purpose of the video, which is just kind of like deburring, chamfering the burrs off the corners there. It's a 2-flute, 3/16 2-flute, 90-degree tip carbide end mill. I think it's running at 10,000 RPM, and I can't remember the feed rate, 30 inches per minute maybe, something like that. And I'm trying to hit as many corners as I can here so that the deburr guys don't have to do too much on it. It's a little bit tricky to deburr this copper with I think they use those rotary burr, high-speed grinders, and you got to be careful because you can gouge into it real easy with those things. So I'm trying to cut as much as I can here for them. So now all we got left to do is put the holes and the engraving in the part. Just rotating it around so you can kind of see what's been done so far. Oh no, we probably can hear that air compressor venting off air. I should have closed that door. I start doing this recording and I don't think about these things till after I'm doing it. So I think this tool's a spot drill. Oh no, that's a 3/8 carbide drill, excuse me. I got to drill those counterbores first. These 2 counterbores I mentioned in the previous video, and I got to make sure a slug, when you drill through, the tip of the drill leaves a slug, and there can't be a slug down in that hole there because I'm coming in here now with a spot drill. Eventually I'm going to go in those holes. But it's spot drilling for all the various those are for the 440 STI threaded holes. And then, of course, it spot drills for the 1032 STI holes as well. That's going down in those counterbores right there with a spot drill. And if that little slug from the tip of that 3/8 drill is left in there, that spot drill is going to hit it and cause problems. Kind of hard to video this with this coolant like that. Doing the best I can so you can see what's happening here. Some of the tools, they throw the coolant off the shank of the tool when it's rotating at the higher RPMs, and it's just like almost impossible to get decent video. Okay, this is just a drill in those little angular, rectangular pockets. There must be a pin or something that's going in there with a threaded shank on it. Because now I'm drilling the 1032 STI threaded holes with this drill. The drill has to be that long sticking out because it's going to go down in those counterbores right there. And here's the tap drill for the 440 STI thread. Although I'm actually milling the 440 holes, the thread mill. So we're getting close to the end here finally. This is the 440 STI threaded hole, thread milling cutter. So what I usually do when I'm milling a thread, particularly this small of a thread, because you can get a lot of push off on this tool, is I'll mill the first hole and then I'll stop the machine and I'll check the hole with the thread gauge. And then I'll let it run through all the rest of the holes and I'll check the final holes. So I kind of figure if it gauged on the first hole and it gauged on the last hole, that everything in between is going to probably be all right. So I'm not going to run through this thread mill takes quite a bit of time. So I'm not going to run through every hole and make you watch every hole. It might take like 30 minutes to mill all those 440 STI holes, because it's actually with this little teeny thread mill, it's taking like 5 passes on each cut going out radially. So it takes I think I have it set to take 60% on the first pass, and then another 15 and 15, and then go to the full size and then make 2 spring passes. I think is the way I've got it going. And here's the 1032 STI thread mill. And then the next tool is the remember in the previous video I made that tap extension after I checked this thread with the thread gauge. So I made that special tap extension for this tool, and I'm tapping, there's holes in those little pockets and I tap them. First I tap those holes in the bottom of the counterbores, and then these holes in the angular pockets. Every thread on this part is an STI thread, but there's just 2 sizes, 440 and 1032. And then here's the last tool, which is engraving. This, I think just because I had the tool already in the holder, I think it's a 1/32 inch, very short stub length carbide ball end mill. That it's kind of like a die sinking end mill, I think they call it. So the cut length is only like a 1/16 of an inch long, the tool itself. So it's a very strong tool, even though it's only a 32nd. And I'm filing it with a very fine file. I think I buy those from these jewelry supply places. Real fine file, and I left the coolant on there because that seems to help with the filing of it doesn't scratch the part with the coolant on there. I just file that a little bit and then hit it with Scotch-Brite. Get rid of those burrs. Those will have to be deburred a little bit more, but that gets the bulk of it. So that's the part complete now. All except maybe some deburr, which I won't do that. The deburr guys here at Centerline are going to do that part of it. So this job turned out to be, actually it's going a lot better than I thought it was going to go. Here you can see it's hard to get photography on this because it reflects light so much, but you can see the detail in those pockets there. This copper really reflects the light. Kind of see the engraving somewhat here. So anyway, that's going to be it for these parts on the videos on these parts. And I hope this is helpful to somebody, and thanks for watching.